Okay, so we are going to continue on our conversation of muscles, and we're going to kind of take a different route this time because last time we focused on the parts of the muscle, and this time we are going to focus on how the muscle actually works. So last time was the anatomy, this is the physiology side of muscles. One of the biggest things to understand about muscles is that they actually only work in one direction, which for some people that's not something that they usually consider because we know that if we move in one direction, we typically can move in the opposing direction as well. But that is why we have so many muscles, is because once a muscle takes us in a certain direction, it is done. It cannot assist or move us back in the other direction. So when we talk about muscles, they can only pull. That is the only direction that they work in is in a pulling action. And once they pull us to get us to a particular position, now we're going to have to rely on a completely different muscle to move us back to a different position or our starting position. So keep that in mind as we go through today that muscles can only work in one direction, and that is in a pulling type motion. So the first slide that you have talks about nerve meeting the muscles, and that is going to be referred to as a neuromuscular junction. And then it also has a different name, myoneural junction. And this is not uncommon where we have structures or parts that are going to go by multiple names. Both of them are completely acceptable, just whichever one you prefer over the other one. So the NMJ stands for neuromuscular junction, and then you can see the myoneural junction as well. One of the things to understand, and you've got the picture there that shows the nerve. So at the top, you can see the nerve extending down and the multiple branches of the axon that are going to come very close to the muscle. The thing to understand is that they do not come in direct contact with the muscle. There is a little bit of a gap between those two structures, and that's important because you don't want the nerve to be in direct contact with the muscle, or the potential for there to be constant stimuli would become or would play into the picture. And obviously we don't want our muscles to get the sensation to contract all of the time. So there is a little bit of a gap between the two structures just to eliminate that from happening. So I'm going to talk through the list of those different structures. You guys can add and take in notes. And there is a second slide that is titled muscle contractions. It is the very next slide. Um, those two kind of go together. So starting with the motor neuron. The motor neuron is going to be the name that is given to a nerve that is going to serve a muscle. So if it has a connection or a link to a muscle and is going to relay the stimulus to a muscle that it needs to contract, then it falls into the category of being a motor neuron. Motor neurons are typically going to carry out some sort of movement. So when that stimulus goes from the nerve to the muscle, it's going to tell that muscle that it needs to contract, and you will see some sort of movement within the body. The second one that you have there is the motor end plate. The motor end plate is going to be where the axon terminals of the nerve are actually going to come in contact with the other side of this connection. And that is kind of shown better, I think, in that pull-out picture. So you have that pull-out that sits at the top right, and you can see where that motor end plate is in that picture, like I said, a little bit better than in the large picture. Then we have what is known as the synapse. The synapse is the space that you guys have between, and synapse, synaptic cleft. It's talking about that space or that region that you have between the nerve and the muscle itself. And I indicated just a minute ago why that gap is important. You do not want the nerve and the muscle to be in direct contact with each other. You do need a little bit of that gap or that spacing, just so that they don't constantly give each other information or feedback. From the synaptic cleft, we have the synaptic vesicles. Now, the vesicles are actually held within the nerve cell itself. And if you look again at that pull-out picture, you'll see what look like kind of little bubbles and little spots within the bubbles. Those vesicles are going to be where your neurotransmitters are going to be held within the nerve itself. Neurotransmitters, these are going to be hormones of the nervous system. So if I say hormones, we think about chemicals of the body, how we relay messages through the body. Hormones are released. That's how different body parts communicate with each other. When I say neurotransmitter, it is still a hormone, but now we are just being very specific that it is a hormone of the nervous system. So embedded in those little bubbles, those vesicles of the nerve cell, you are going to have those neurotransmitters, the hormones of your nervous system. And they are held there until the impulse comes in that the nerve needs to deliver a message to the muscle. And at that point in time, those vesicles will actually break open. And when they break open, they release their neurotransmitter, and that neurotransmitter will now cross that synapse. It will move across that gap and make its way over to the muscle. And that's really when this process of the muscle contraction is going to begin. Okay. So in this picture, you see the nerve coming very close to the muscle, but not coming in contact with it. Within the nerve, we have the neurotransmitters or the hormones that are going to communicate or relay to the muscle when it actually does need to contract. Now, if you go over specifically and focus on that second slide, which talks about muscle contractions, in this particular one, it starts off with the term acetylcholine. Acetylcholine is the specific neurotransmitter that is going to be held in the motor neuron. And you'll notice that it gives the abbreviation of ACH. Hormones, neurotransmitters typically have long names, and so they do get abbreviations. So if you see that ACH abbreviation, it is referring to that acetylcholine that you have within your nerve cells. So acetylcholine is designed to make its way over to the muscle and begin the process of the muscle contraction. So it kind of talks through the process, talking about the nerve is going to release that acetylcholine. The acetylcholine is going to move over to those motor end plates and latch onto them. And that is going to then be transferred over to the muscle, which is going to tell the muscle it needs to start the process and doing the things it needs to do to carry out the muscle contraction itself. Now, in the muscle, one of the big things that is held within the muscle that is very important to this process is going to be calcium ions. In discussions about calcium, when we talk about that, typically people immediately go to the bones. They hear anything about calcium and we associate that with bone health, bone strength, and things of that nature. And that is very true. It is very important for bone health and bone strength. But the reason that we store that calcium in the bones is because if you ever do not have enough calcium in your diet on a daily basis, you can't run out. You have to have a stockpile of calcium on hand at all times because that is the very basis of how a muscle contraction takes place. So if you don't have enough calcium in your body, your muscles would not be able to contract. And obviously, that's of huge concern, not only for movement, but if you think about your heart being made of muscle, it obviously cannot stop contracting. So the bones by design are going to be these massive storage tanks of calcium. So if you don't get enough calcium in through the foods you're eating on a daily basis, now we have a completely different hormone that can be released into the body. It will actually tell your body to break down your bone tissue. And by breaking down your bone tissue, it releases that calcium into your bloodstream. Calcium will circulate until it makes its way to the muscles. And now that calcium will be delivered to your muscles so they can continue to contract. So anytime that you don't have enough calcium in your diet, we're stealing that calcium out of your bones to make sure all of your muscles, especially the heart muscle, will continue to do what they need to do in order to keep you alive. Now, it can work in the reverse. So if you have an abundance of calcium in your diet on a daily basis, now you have a second hormone that will tell your body to store that, and you will take that calcium from the blood and you will turn it into bone tissue so that you can replenish those reserves that you guys have. All right. So from there, it talks about muscle relaxation. Once you guys have a muscle contraction, you obviously don't want that muscle to continue to contract past a certain point. So once you're done with the movement, whatever the case might be, you want the muscle to stop the contraction process. And so now we are going to rely on something that is known as acetylcholinesterase. And what acetylcholinesterase does is it will break down acetylcholine. So acetylcholine is going to tell your muscle to contract. Acetylcholinesterase breaks down any remaining ACH after you want the muscle contraction to end. So that is, or will help the process of telling that muscle it needs to stop contracting and you can go back or return to a different position. If you go to the next slide, it talks about the different types of muscle contractions, and there are 4 that are identified there. So you have isotonic, concentric, eccentric, and isometric. Now, in looking at this, isotonic refers to a muscle contraction and changing the length. And the 2 types of isotonic contractions are the eccentric or the concentric. So isotonic just tells us that the muscle is going to contract and change its overall length. The 2 examples of that would be eccentric with the lengthening and the concentric, which would be a shortening motion. Isometric is a different type. This is going to be a situation where a muscle is going to contract, but it doesn't change length. So if you think of an isotonic muscle contraction, if you pick up some free weights or you're doing a bench press and you are actually moving the bar up and down through that bench press, that would be isotonic, because in order for you to lower and push that bar back up, the muscle is contracting and it's changing length in order to get that to happen. On the side of isometric, this would be a situation if you went up to a wall and you pushed against the wall, your muscles are contracting as you push up against that wall, but chances are you're not moving the wall anywhere. And so while the muscle contracts, it's not changing length because what you are pushing against is not going anywhere. So there's a difference between those 2 different types of muscle contraction. Isotonic, you are going to see actual movement. In isometric, muscle is going to contract, but you are not going to get any movement through the action that you are doing. The next slide that we have talks a little bit about your smooth muscles. And I told you guys when we started this particular chapter that so much of our focus was going to go into the skeletal muscles just because of the sheer number that we have. And so we have spent most of our time on the skeletal muscles, talking about what they're made up of, how they work, and things like that. This is just a little bit of a focus on the other types of muscles that we have within the body. So if you look at the first one for smooth muscles, one of the things with smooth muscles is that they don't have the same organization as your skeletal and your cardiac. So skeletal and cardiac are going to have those alternating dark and light bands. So you are going to have that striation appearance. We talked about that in the first lecture. You don't get that with smooth muscle. So because the actin and the myosin do not alternate in the same fashion, you are not going to see those stripes or those light and dark areas within the muscle tissue itself. The other thing with your smooth muscle is that it is going to have a spindle type shape. And what that means is that it's going to be wide in the middle and then it tapers at the ends. If you think of what an eye looks like, so at the middle of the eye, that is where it's the widest or the thickest. And as you move to the sides, our eye kind of tapers down and becomes more narrow. That is going to be that shape of the smooth muscle. And because of the shape of those, they actually nestle together with each other very well. So the thin tapered end would meet up with the thick end of another smooth muscle cell, and they just stack and layer in that fashion. So they are designed in a way that those cells can kind of come together and position themselves. Like I said, nestling is probably the best term to identify how those cells fit together. With the smooth muscle, if you go on to The next slide just talks a little bit about the muscle cell a little bit more. One of the biggest things that I want to kind of focus on with your smooth muscle is that this is going to be the muscle type that does not have to be focused on by us. We do not have to tell these particular cells to work. They are going to be linked to the brain, and the brain is going to take over their function and make sure that they work when they're supposed to work and how they are supposed to work. So with the smooth muscle, this is typically going to be found in our hollow organs or our other body parts that, like I said, we don't have control of. It talks about the iris of the eye, the walls of the blood vessels, as well as your internal organs. And you guys can think of other structures and body parts that work on their own and you don't have to tell them to do anything for you. But those are going to be your smooth muscle fibers that are going to be carrying out that function for you guys. If you go into the cardiac muscle slide, as we already mentioned, it's only going to be found in the heart. And that is because your muscle cells that take care of the heart have to work in a very specific way. And because of how they have to function, we have to make sure that you don't get cramps in the muscle heart or the muscle cells. Because obviously, if you would get a cramp, you guys know what a cramp is when you get it in a leg or an arm and how it limits that muscle from being able to do anything else. Obviously, that can't happen within the muscle of the heart. So these particular cells have been designed in a way to prevent that. And one of the biggest things with that is going to be not only the intercalated discs, but also what is called the refractory period. And we'll get to that refractory period here in just a second. Intercalated discs, we touched on last conversation as well. Thick discs or bands between the cells that are going to unite the cells so that when one contracts, they all contract at the same time. This is going to produce the amount of force that is necessary to keep blood moving in a forward direction. The other thing that we have within the cardiac muscle, the refractory period. This is going to be the time frame because in a muscle contraction taking place, you have a lot of moving parts. So the muscle is going to have to contract, it shortens down in size. There's things that need to change, that calcium is released, the acetylcholine is released. You have all of these things that are happening. When the muscle contraction is over, all of those things that cause the muscle contraction to happen, all the parts that moved and changed their position for the muscle contraction to happen, they have to get back to their starting points. And so when we talk about the refractory period, that's what it is. It is the time period that is given to a particular structure or body part for anything that moved from its initial starting place to be able to get back to its starting place so the next contraction can happen. Now, when we talk about refractory periods, that took me 30 seconds to kind of introduce. Think about how quickly your body parts have to get that done. Because in the case of your cardiac muscle cells, they have a longer refractory period than your skeletal muscles would have in order to get that done. And we're still talking about fractions of a second. So this is not something, when we say longer refractory period, we're not talking about 10, 15 seconds. We're not talking about a couple minutes. We are still talking about fractions of a second, but they get a little bit longer than what your skeletal muscles do to get everybody back to their starting points before the next contraction will happen. Because the skeletal muscle does not get as long, that is what allows for the potential of cramping to happen. With the heart muscle getting that little extension of time, it takes that kind of out of the picture so that we don't have to worry about that cramping happening within the muscle tissue. The next slide that you guys have talks about the characteristics of muscle tissue. And I wanted you guys to kind of be able to see this just side by side. The length and the diameter, I'm not too worried about that. And here's the reason why. When you get into the smaller units of measurement, centimeters, you guys can see that, you know what a centimeter looks like. You can look at that on a ruler. When we get into the micrometers, that's incredibly small. That is a length of measurement that I can tell you what it is and how we get there, but to actually be able to envision that, we can't really do. So I want you to understand that they are very small units of measurement, but I would never expect you guys to know that or have that committed to memory. The big things that I want you to take a look at here would be the locations, the major function, who has striations and who doesn't, and the mode of control. So is it something that we're able to control and tell it when we want it to work, or is it going to be done through the brain and the brain kind of taking over that process for us? Now, the last part of this particular packet talks about muscle actions. So we know that when a muscle contraction happens, we're going to see some sort of movement within the body. And I led off today talking about the fact that muscles can only work in a pulling direction. So if you look at the slide that talks about origin and insertion, it talks about where a muscle is going to begin and where a muscle is going to end. That's essentially what origin and insertion are. But if you look at the definitions that are associated with those two, origin is the immovable end and insertion is described as the movable end. So we're not talking about starting and ending, we're talking about the type of movement that we see. Now in the picture, it gives you the example using the bicep muscle. And with the bicep muscle, you'll notice that on the scapula and the top of the humerus, you can see where the bicep muscle is going to originate. But if you track that muscle down, it's actually going to move over to the bones of the lower arm, and that's where it ends. So when we talk about muscles carrying out movement in the body, one of the biggest things is that the beginning of the muscle and the end of the muscle are going to have to happen on opposite sides of a joint. So you can see that happening here. We start the shoulder and then it's going to move past the elbow. It's actually going to finish on the other side of that elbow joint. That is the only way that we can see movement happen when a muscle contracts, is if it begins and ends on opposite sides of a particular joint. So we have that going on here. Now, with the origin being the immovable end, if you think about it, the start of that bicep muscle is going to be up in the shoulder. And when that muscle, that bicep muscle contracts, if you guys had that bicep muscle contract, the humerus doesn't go anywhere. The shoulder doesn't go anywhere. There is no movement in the upper part. But where do you see that movement happening? It's the lower part of your arm that's actually moving. So that's why we see those definitions of immovable end and movable end. Wherever the muscle begins, that's not where the movement's going to happen. That is actually going to come on the other side of that joint. So just to clarify the difference between the origin and insertion of the muscle. The last slide that we have talks about muscles working together, and it gives you 3 different definitions. So it talks about the prime mover, the synergist, and the antagonist. Again, going back to my opening statements of muscles only being able to pull, they have to be able to work together, because if I can only pull, that means that when my bicep pulls and I bring my arm here, bicep is done. It is not going to be able to do anything to get me from this position back to a different spot. So muscles have to work against each other, where one pulls you in one direction. So my bicep got me here. Now I'm relying on my tricep to pull in the opposite direction to get me out of this and to a different body position. So prime mover, that is going to be whatever muscle causes the initial movement. That is your agonist. So if I have my arm and I pull in, okay, my bicep was my prime mover because my bicep was the muscle that got me to this position. But the bicep is done now. It pulled, got me here. It's not going to be able to do anything to move me out of this spot. Now I'm going to have to rely on an antagonist. And if you think about what an antagonist is, it's something that kind of works against you. So an antagonist, like I said, is going to pull in a different direction to get me back to usually my initial starting point. So bicep and tricep are great examples of antagonistic pairs. Two muscles that are going to be able to pull in opposing directions. So one will move you into one spot, the other one will move you back or out of that position. Now, synergists are going to be muscles that are going to work with the prime mover. Synergists are usually smaller muscles, and their job is to kind of help provide that finer movement. Prime movers are usually large muscles. And so being able to pinpoint an exact spot or location with fine movement can be a little bit more difficult with those prime movers or those larger muscles. So synergists are going to be smaller muscles that kind of help anchor, hold that large muscle, not in place, but just refine its movement a little bit. So if your pencil is sitting on the tabletop, those synergists are going to help you be able to pinpoint the exact location so you can target whatever item you are trying to pick up and get it with the first try. Likewise, with the synergist, these are going to be the muscles like with handwriting. If you guys think about what your handwriting looked like when you were in kindergarten and what your handwriting looks like now, and for some people there might not be much change in what the letters look like, but the size of the letters probably has changed. When we are little and we're first learning how to write, usually our letters are very large. And a lot of times we don't close our letters. So if you're writing an O, you'll make the circular motion, but you don't fully close it. There's a little bit of gap. Now, the reason for that is because those synergists are not well developed. Your prime mover is doing most of the movement, and because they're very large muscles, getting that fine movement. So being able to make those letters small, being able to pinpoint where you started the letter so that you can finish and close that O, that is not developed yet. And so that's why we typically see handwriting change as we age, because as we write more and more, those synergist muscles become better developed, and now we can pinpoint where we started our letters so we can finish and close it off. We can now make our letters smaller because those little guys are giving us, or those smaller muscles are giving us that finer movement that we need in order to see that transition happen. All right, so that takes us through our muscle side of things. Once you guys watch the video, complete your assignment. Again, we're going to stay to our week due date, so you have 1 week to watch the video and then complete the assignment and get that submitted to me. Cannot stress enough that if questions arise, please let me know. Shoot me an email. The Sioux City Schools one will get you a much quicker response. So if you need anything, reach out to me, and I will get back to you as soon as I possibly can.